Let's go to maybe our first big application problem of the course. So it can be an application of waves in the ocean to some extent. Why is this? Why do I like this? I mentioned, but let me write it down. This is a good place for us to think of. And put it as good for learning. Asymptotics with differential operators, which I like calling this reduced modeling, which is getting a simplified model, a simplified differential equation. We can also see some asymptotics with solutions of differential operators. Okay, and in particular, it's a good place for us to play with. Give you one example of multi-scale analysis, which is, I find a very nice mathematical idea of where you generate new independent variables in different scales and you see how they interact. So it's a very nice setting. Okay, so let me recall the problem with the equations. So let me do a picture with the equation. Let's see if I do the right spacing. So I have here the bottom. At first, I'm drawing a bottom topography of like the ocean, which is smooth. There's a point where we can consider not smooth, like a step. I have the wave, elevation. Okay. I'm going to put, as you will see, sometimes I put the origin at the bottom, sometimes at the top. It doesn't really matter. Okay, I'll try to remind you when I change. I hope I do remember. So I have Laplace's equation in here. I have Neumann condition in here, which is basically d phi scalar dn is 0. And let me remind you, we're doing, excuse me, we're doing potential theory, which means that uv is the gradient of phi. So this is our velocity vector, and phi is the potential. So u and v, horizontal and vertical velocities. So we, instead of using two independent variables, we're going to use just one, which is the potential. This is due to physical properties of the fluid, incompressible, rotation, blah, blah, blah. But this is not a fluids course, so let's take the PDE, and it's a free boundary problem. So I have to define the curves. Actually here, I forgot. This is a fixed bottom. This is our free surface. I'm already writing it. No, first I'm writing it. Yeah, I just did the dimensional case. We're going to do today the dimensionless case. And over at the free surface, we have these two complicated operators, boundary conditions. Whoops. Okay, let me maybe write this velocity vector here on top. And because this is an evolution problem, these are my initial conditions. Sorry, I still have this little allergic cough following me. Okay, so look at this problem. This problem it has a simple part and a very complicated part. Of course, the whole problem is then very complicated, right? The domain omega, where I'm solving Laplace's equation, right? We just talked about Laplace's equation, so this is a problem which I like also because we talked about waves, we talked about Laplace's equation, now there's the two things coming together. So the domain is a time-dependent domain, right? So it makes it already difficult. I don't know in the next, say, instant of time where I'm going to apply my PDE. That's why it's called a free boundary problem. Why? Because this free surface or free surface problem, because this boundary here, where I'm solving Laplace equation, is changing in time, because this is my wave elevation. This is what we call wave elevation, right? So as this wave moves, my domain changes. So that makes the problem very complicated. So I'm solving Laplace's equation with a homogeneous Neumann condition on the bottom, which means that my bottom topography is fixed and impermeable because there's no flow, there's no normal velocity in this way, right? That's a simplification, but still it's legitimate and makes the problem not that much simple. Other cases makes it even more difficult. So this boundary is fixed, this boundary changes. H0 is a typical depth, and this is my free surface conditions, which in fluids we learn where they come from. Here it's a PD's course, we just sort of accept it. We have the evolution in time of the wave elevation and the velocity potential. It's a nonlinear problem, and because it evolves in time, we need the initial potential at the free surface eta 0 and the free surface eta 0, and we let this problem go. Okay, so we're going to learn from today on first how to dimensionalize this problem. That is, put it in dimensionless variables, because say this typical depth here, as I mentioned last class, this typical depth can be centimeters or thousands of meters, for example, for a tsunami, right? This wavelength here can be hundreds of kilometers if it's a tsunami. The wave height here, A, as I mentioned, could be centimeters in my bathtub or my pool. As I mentioned last time, I don't have a pool, but in my pool, or meters in the ocean. Okay, so these are all scales, and I have a scale for the variation of the bottom. So I'm going to use these scales to dimensionalize the variable, so it doesn't matter. You'll see the PDE doesn't matter so much if I'm in my bathtub or in the ocean, because I'll have parameters that controls it, and I'm going to order these parameters in terms of epsilon, which is something us mathematicians like, right? Something that's small, we call it epsilon, order of epsilon. This is the first step, and that helps us to, in an educated way, know what's big and what's small. And knowing what's big and what's small, we know which terms of the PDE are more relevant at first than others. And how can we then maybe throw some of these terms away and get a simplified, yet complicated, but simplified PDE, better for theory, better for numerics. That's what we're going to be seeing in the next classes. So all physically motivated, but the mathematics is this. Asymptotics of operators. Also, we're going to do some asymptotic solutions, and we're going to see problems with multiple scales. So we call it multi-scale analysis. Okay, so let me define then, I think I mentioned everything. Let me define, I think this is what I already mentioned last class. So let's choose scales, okay? So we call this dimensional analysis. It's a sophisticated name for something very simple that at the end is just calculus, it's just a chain rule. But choosing the scales, it's not that easy to teach, I think. It's by experience. You have to see many problems and you start learning, oh, for this problem I scale like this, for that problem I scale like that. But once you choose the right scaling, it's calculus. It's just change of variables. Okay, so let's go. So dimensional analysis means let's choose the dimensions, relevant dimensions, and dimensionalize our variables. So let me put like this, dimensional analysis. And here are dimensionless. This is important. Without dimensions, I dimensionless variables. Which ones I'm going to choose? I'm going to start like this. X is equal, so let me write it and then I'll explain it. Okay, let me basically just quickly copy. Okay, I have some more, but let me stop here first. These are the independent variables. And then I'm going to dimensionalize the dependent variables. So X is going to be scaled. So this one, the tilde one, are dimensionless. Because, look, let me write like this. Sorry, I'm going to be almost like pedantic, right? Doesn't matter, just for the first time. Because if X is my original variable, okay, and I am running here over, this is 100 kilometers, I'm running over 100 kilometers, X tilde, I'm going to go from 0 to 1. It's dimensionless. Because as soon, if I put this 100 kilometers, my typical, sorry, I pointed at the wrong wavelength. Sorry, go back. The wave is 100 kilometers, right? The tsunami. I just had my hands in the wrong place. So if this is 100 kilometers, the tsunami, in X tilde, I'm going to run from 0 to 1, right? Because as X runs from 0 to 100 kilometers, and I divide by 100 kilometers, this guy is now dimensionless, and I've normalized my typical length. If my problem is a tsunami problem, my typical length is 100 kilometers. If my problem is like waves, as I've been jokingly in the bathtub, it's 10 centimeters. But then it doesn't matter. If it's 10 centimeters or 100 kilometers, X tilde varies from 0 to 1. I've normalized. Okay? Same thing for the depth. Okay? This H naught here, my H is a little bad. I choose my typical depth. Is it the bathtub or is it 4,000 meters in the ocean for a tsunami? At the end, we won't care. In Y tilde, we won't care because it's normalized. And for the time, so here's where you gain experience, right? You could have said, André, okay, for the time, let's pick a typical time. In the bathtub, it's seconds. In the ocean, it's hours. But look, so that we don't add too many parameters, because at the end, we want to have the least possible number of parameters, then since we have the shallow water speed, remember square root of GH0, and so this guy is already connected with this guy, because see? So I'm going to choose my typical time, the typical time of a tsunami in the linear regime, but whatever wave I'm caring about. So since this is speed and this is length, so in our notation we do like this. Look, or let me put it like this. This has units of length. Down here I have units of length divided by units of time. So this has units of time. okay? And like that, I'm saving, not adding more stuff. I'm already using somehow h0 as a reference for my time, of course, through the shallow water speed. Okay? Then I have that eta. I think I don't have to explain this, right? Just look at the figure here. No words needed, right? Typical amplitude. So this is my dimensionless wave amplitude, the normalized wave amplitude. This one, when I saw it for the first time, I find it more difficult. I wouldn't at first not have guessed this. Okay, I'll come to this in a second. And we also dimensionalize the topography height like this. Okay, so let me comment these two. These two are important maybe to comment. Let me comment this one, which is easier. This is easy. So I'm going to have now a dimensionless topography varying in some reference scale that tells me if the topography is fast with respect to the wavelength. Because remember this, if I have something, we're going to be seeing things like that. Look, if I have this, or if I have that, that means if this guy here is an epsilon, or 1 over epsilon, I have two very distinct regimes. This is a slow variable, and this is a fast variable. And actually, we're going to use this when we do multiple scales. So this, let me put it here, is a fast variable, and this one, no, the other way around, sorry. Slow variable, and this one is a fast. Why this is slow? Because as x, let's think that epsilon is 10 to the minus 3. As x tilde goes from 0 to 1, because I've normalized it, this guy just goes from 0 to 10 to the minus 3. So it's a slow variable. It's something that changes very slowly, and that sometimes is useful for a problem. On the other hand, there's other problems where we will see a case where the topography varies very fast. So if this is 10 to the minus 3, epsilon is 10 to the minus 3, this is 1,000 x tilde. So when x tilde changes only from 0 to 1, say over a tsunami of 100 kilometers, this guy could have varied very much because it went from 0 to 1,000. Okay, so this is a fast variable and this is a slow variable. So it will depend if we have a fast topography or a slow topography, depends on how the wavelength of the bottom relates to the wavelength of the wave. The wavelength of the bottom relates to the wavelength of the wave. So you see that with the epsilon on top or the epsilon on bottom, I'm already controlling which physical problem I'm talking about. And that's very important for the PDEs, as you will see. Right? If I have an epsilon on the bottom, the epsilon on top, and so on. Okay? So you see already the effect of using dimensionless variables and eventually putting epsilons into the problem. This case here, how do I know? I personally, when I read this for the first time, say I think in Witham's book, I didn't understand. I mean, how would I have guessed that this gives me a dimensionless potential? Okay? So one thing for you to check is this. Well, let's see if it's right, right? To see if it's right, I do this. Look. This is the units of a potential, right? What is the units of a potential? Well, the units of the potential should be such that if I differentiate it in space, I get a speed. Here it is. Right? So look, this is very simple, but it's just maybe new to you, as it was to me at the time, and it's basically just organizing mentally things, but it's very simple. So if this has to have units of speed after I differentiate it with respect to x or y, what does it mean to differentiate something with respect to x or y? It's like d phi dx. So I'm dividing by dx, right? So this means this has to have units of length over time, which would be the speed, times length, so that when I differentiate it, I get the speed. You agree? Okay, so I can erase this, and I can put here squared. Okay, and then I'll leave it to you to check that this has the right units. Okay, that it has the units of length squared over time. Okay, you agree with that? Now, you still could ask me, but why? How would I have guessed that I need to have the gravity times the wavelength times the amplitude divided by the speed? I wouldn't have guessed that, as I told you when I did this for the first time. But then, what you can do, that's the way I would do it, is just call this parentheses here. It's going to be a number, right? Because this is a number. That will be my reference potential. And the way to do it is when you substitute, this is the way I would do it. When you substitute this, and this into the equation, leave it, put something here, and you will see that the equation at the end becomes, you can clean up parameters the best way if at the end this is equal to this. Okay? And that's what we want. We want at the end to be left with the minimum numbers of parameters, dimensionless parameters. And I'm going to write now the dimensionless equations, and you're going to see that this problem leaves us with 3 parameters, which is kind of a lot, but it's good. You'll see, because I can tune many different things. Okay, but is that clear? If you don't know how to choose this guy, leave it open, and then you start collecting A, lambda, G. You collect everything, and then you're going to see that a bunch of guys are going to pile up in front of phi. Okay, and then you check the units, say, fine, that's the dimensionless potential. Okay, all right, so here's the dimensionless equations. Okay, let me erase here. Let me put this here so I can get more space. Okay. All right, so here are the dimensionless potential theory equations. It's like this. Oh, and that's typical things in papers. Drop the tilde. Okay? Right? So you put it with the tildes and then say, now forget that I've changed abusive notation and forget the tildes. Okay? So this is actually the dimensionless variables. let me write here. Yeah, let me write here. Very important. I'm going to write the most important thing, I think, which is I'll write in orange. Okay. Okay, so what I did is basically calculus, right? Change of variables. You substitute all these guys into the previous equation, and you say instead of solving now for x, I'm solving for x tilde. Instead of solving for eta, I'm solving for eta tilde. It's just cranking the wheel, okay? No deep thinking. You collect terms, that becomes a junk. You organize things, and it collapses onto this. Okay, and now, since I didn't want to change chocks, let me change chocks now to make sure I highlight things. Look, I got a beta that came up here. I got an alpha that came up here. A beta here. Alpha. Alpha over beta. Beta over gamma. Okay? Oh, and very important also, alpha here, and gamma here. Okay? So look at this. I have my dimensionless potential theory equation, which will allow me to do many things. Okay? So the first thing, let me tell you, now I can show you in a very clear way, mathematical way, the two sort of sources of nonlinearity of the problem. And actually, alpha is our nonlinearity parameter. Why? Because alpha multiplies all the nonlinear terms. Look here. Nonlinear term, nonlinear term, nonlinear term. Okay, so if I make alpha equal to 0, is my educated way, systematic way to linearize the problem. But look, alpha is also here. And this is very cool. This is very nice. Because if I make alpha equal to 0, I linearize the terms of my operator, right? The most complicated. And I also tell you that, look, you are now allowed for the linear problem to apply your free surface operators at the undisturbed level y equal to 1, because this becomes 0. So that means that over here, look, y equal to 1 would be, in the original problem, would be y equal to h0. But since I've normalized, the depth, the reference depth now is 1. Right? So you see that linearizing the problem gives me let me put it the other way. There are two sources of nonlinearity in this problem. The first one is obvious, nonlinear terms. The second one is obvious after you see this, which is the fact that I do not know where I'm going to apply my differential operator is a source of nonlinearity. The fact, in other words, that I have a free boundary problem is another source of nonlinearity. And if I linearize my problem, that means alpha equal to 0. As a bonus, I get that I can apply my differential operator, free surface differential operator, at the undisturbed level. Still, the linear problem is going to be difficult, you will see, but simpler than this one. Okay? Cool? Now, second parameter. This parameter here, beta, we call it the dispersion parameter. You will learn, maybe today, maybe next class, why the name dispersion. It has to do with Fourier analysis of this problem. But look, when beta becomes small or goes to 0, it means that I'm in the shallow water regime or the long wave regime. Repeating, I'm in the shallow water regime or the long wave regime if beta is epsilon or goes to 0. Okay? And finally, this last term here, which we'll forget about it soon for the time being, it's related to the topography. It tells me, basically, if, as I mentioned here, if I have a rapidly varying topography or a slowly varying topography. Remember, for the problem where we got the Eikenau equation, right? When we deduced the Eikenau equation, I assumed as a hypothesis that our medium was slowly varying with respect to the wave. Or, in other words, that we had short waves with respect to the varying medium. Okay, and then we did geometrical optics. So this would be this case here, slowly varying medium. Right? And soon we will do a problem which is in the other extreme, which is a rapidly varying medium, where we're going to apply multi-scale analysis. That is the analysis with multiple scales. Right? This is just advertisement of things coming in the future. So for when we deduce the famous KdV equation, Korteweg's-de Vries equation, the scaling, or the regime, as we say, is going to be flat bottom, so there's no topography. This gamma does not apply. And alpha and beta are both order epsilon. They're not 0, they're small. So therefore, the regime of the famous KdV is called a weakly nonlinear regime, which means it's nonlinear, but the nonlinearity is weak. It's epsilon. Weakly nonlinear regime and weakly dispersive regime, because the beta is also 0. Is also small. It's non-zero, but it's also small. Okay? Okay, so let's continue. Okay, so and depending on how I choose all these, the regimes, as we'll see, I'm going to start talking about Ansatz. Ansatz is a German word which is related to a little bit to proposing something like to an educated guess. Educated guess is that I write the way I think the solution looks like, and immediately I tell my readers or my audience, right, in a paper, in a book, or in an audience, what I'm thinking. Oh, André is thinking about the waves like this, like that. Will it work or not? We don't know, but this is what I call the educated guess. And with the ansatz, you try to simplify the problem, okay? So you will see that depending on the ansatz I put in these equations here, that's why this sometimes I call jokingly, it's like the mother equations or the parent equation for other famous equations. Because from this set of equations here, I can extract asymptotically through this first item here, I can extract the KdV, the famous KdV. I can extract the famous Boussinesq system. I can even extract, which I won't have time in the course to do, but I'll just indicate a little bit, the famous equation from quantum mechanics, but that has not the same meaning, of course. The Schrödinger equation also comes out of here. So, and if I even simplify further, I get the shallow water equations, which I taught many classes ago. So this equation here is beautiful because it leads to many, many famous systems. And, and not so long ago, this was considered a very difficult problem and so on, to the point where you will find in the internet Feynman saying that to study water waves, to give this as an example of a waves problem was a terrible idea because it's too complicated. But I think now, of course, Feynman was a genius and so on, but it was many years ago, many decades ago, and now it's actually, I think it's the contrary. I would say this is an excellent playground to learn about different waves. Okay, and that's what we're about to do. Okay? Okay, so first exercise in reduced modeling. Which is basically simplifying our PDE system, right? Okay, so I'm going to do, so if I ask you, say, okay, tell me, how does this equation here look like, for example, in the limit as beta goes to 0? Is it easy? Alpha equal to 0 is easier. Alpha equal to 0 is just plug alpha equal to 0 here, plug alpha equal to 0 here, alpha equal to 0 here, here and here. The alpha equal to 0, which is the linear regime for a dispersive system, because beta is non-zero, so it's still dispersive. That is easy. But if I ask you, do the limit beta going to 0, I would be in trouble. Because look, if I put beta equal to 0 here, I'm already making the Laplacian funny looking to start with, right? But okay, maybe, okay, maybe I can do. But how about here? Right? So what's going to happen here with these guys? So we're going to learn this now. There are many ways to do this, right? And it's a very good excuse for me to teach some mathematical things. So we're going to see now basically how we can do harmonic extension. Say if we start the problem with this phi 0 at the top, right? That's basically the Dirichlet data for this problem at the top. Right? At least at time 0. It's the Dirichlet data. So how do I do the harmonic extension? Which means, how do I get it inside? Right? And there are many ways of doing that. So we can do it through a power series expansion, as we will do now. And later on in the course, I'll teach you something which I find also very beautiful, which is a Dirichlet to Neumann map, which is actually a pseudo-differential operator, blah, 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 that also, through a Fourier integral, does the job for us in certain cases, not in all cases. Okay? All right. So reduced modeling is, how do I simplify my PDE in a scenario like this for alpha and beta small? Okay. Okay. So let me write things when I say educated this, educated that. Basically what I want to do is a systematic simplification of the PDE system. Okay? So basically I want to see when alpha and beta goes to 0, right? In the limit, in that limit. And we will start with the flat bottom case. Okay. And our regime is shallow water, long waves, which then is expressed by this parameter, and weakly nonlinear waves, which means alpha greater than 0 and much smaller than 1. Okay? And I forgot to mention something. As I'm writing here, I just reminded myself. Let's come back here, right? I've already mentioned about the shallow water, but look, the problem is linear if the amplitude, as I mentioned before, over the depth is small. So that's why a tsunami starts in a linear regime, because the amplitude of a tsunami is 1, 2 meters, but the depth is 4,000 meters if it's in the middle of the ocean, right? Whereas a wave, a little wave in a puddle on the sidewalk could be nonlinear because the depth and the amplitude, it depends where you are, okay? I mean, the relative size of things. Okay, so here's our ansatz. So the ansatz I'm going to make for this regime, so this is the important thing, see? This is our regime. Okay, so it means we have like this, long wave, over a shallow bottom, right? So we have this long wave. So the ansatz is this. I don't know much about the problem, so I'm pretending I don't know much about the problem, and I want to do a power series expansion like Taylor series near the bottom. So this is the ansatz. Okay, and if I left the room and I said, look, tomorrow we're going to think about this problem, try to understand what I'm thinking. Okay, so try to understand what I'm thinking. Well, I haven't written much, but there's already some information here. Okay, look, in my dimensionless problem, even though I'm in the shallow water regime, my depth is, reference depth is 1. Okay? So what this says, look, I'm going to read this now. This is already something saying a lot in a mathematical language. Now let's read it in English, right? So this is an expansion near the depth, near the bottom. So this is basically an expansion. Because look, I have this. So the bottom is y equal to 0. Right? So this is an expansion. So I'm doing an expansion for y, say small, at least smaller than 1, right? Near the bottom. So I'm going to try to figure out an approximation for my harmonic function which satisfies Laplace's equation in here, and saw a Neumann condition here. Okay? So this is, as I said, this is an expansion near the bottom because y is small. So powers of something small, formally, it looks like the series makes sense. So in many of the things most of the things, if not all the things we're going to see in this course, the problems are complicated. You cannot prove that the series converges, but you have evidence that the series makes sense, converges. That's this. So, okay? So this guy, if it's small, if this function here is smooth and so on, it will not give us trouble, but we still have to see what we're going to do. And this is a separation of variables after all, right? I'm separating variables. But the main thing is this. Y is small, is near the bottom. So substitute into Laplace's equation, and then the Neumann condition. Excuse me. Okay, so Laplace's equation, we get this. Look. Okay, so if I plug this formally, this just formally, you plug this in, right? We suppose that it converges and so on. You plug this into Laplace's equation to here, we get this, right? This part here inside, and I forgot something. I forgot, let me put it here. Right, it's a power series expansion in y. This is going to give me the recurrence relation. This is what we call the recurrence the recurrence relation. So this is a power series. Since this has to be 0, all the coefficients of this has to be 0, right? So that gives us the recurrence relation. This is equal to 0. These are just adjusting. As you differentiate, you adjust the summation. Check this so that you can put everybody together. You'll see what I'm talking about in terms of m. And then eventually we get this. So we conclude this. Right? I'm skipping just some computations, right? You should check it on your own. Look what happened. So I'm skipping just some messy calculation, but simple calculations. So again, get this ansatz, plug it in here, you get this. Organize the indices so that you can put everything inside the parentheses, right? So if this is a power series in y, and this has to be 0 for arbitrary y, small, right? 0.01, 0.02, whatever. This parenthesis has to be 0. This gives us the recurrence relation. From the recurrence relation, we note the following. That these functions here that I don't know what they are yet, right? But I realize that only the even guys only couple with the even guys, and the odd guys only couple with the odd guys. Because look, it's m and m plus 2, right? If m is 1, this is 3. If m is 2, this is 4, 6, right? So therefore, I can say, well, I have only then 2 possible guys to deal with. 0, which is the guy with the even ones, right? Because it actually starts from 0. So from 0, I get couples with 2, 2 couples with 4, right? And the odd ones that all couple with f1. Right, so I'm already simplifying things. I say, okay, I can get all the even guys to depend on f0, and all the odd ones to depend on f1. So therefore, I formally get the sum, and I have the sum of the even guys and the sum of the odd guys. Okay, but then check. That f1 is going to be equal to 0 because of the Neumann condition. Okay? So when you check, what is the Neumann condition? Is d phi dy equal to 0, because it's flat bottom. Okay? So I'm skipping some easy points, right? So when you check that formally, so let me rephrase things. So formally, why am I saying formally so many times? Because I'm not checking the convergence of the series, right? But it looks like it makes sense. So formally, I have that my harmonic function is given by these 2 power series. Okay? But we will check, you can check formally that actually when you impose d phi d0, so d phi dy equal to 0 on the bottom, f1 is 0. So if f1 is 0, this whole guy here doesn't play a role anymore. And if this whole guy doesn't play a role anymore, why do I need to keep the index 0? I'm just going to call this f. Right? It's the only guy that survived. So I'm just going to call it F. Okay? So therefore, we conclude that phi of x, y, t equals the sum and from 0 to infinity okay, so satisfies Laplace and Neumann. Right? This is a power series expansion. Okay, and I don't need the 0 here anymore. Okay, and you see this power series, look, if this function is okay, if this function is smooth, and suppose has all the derivatives, right? I have, small parameter at the end, this guy, it looks like formally this series converges. But in generality, we might not be able to prove it, okay, at least. Now, we need to satisfy approximately the free surface conditions. Okay, so to some extent here I haven't done any approximation, right? Because it goes from 0 to infinity. Now we're going to do approximations. We're going to do truncations. Okay. So okay. So at the free surface, we have y equals to 1 plus alpha eta of xt. Right? That's the definition of the free surface. Moreover, phi of x of y. I'm now writing the first few terms of my power series expansion. As soon as I get away from the board, we will discuss this. Okay, so look what I did. Got a little bit of water. What is my free surface conditions? It's here. So let's look at this board here. Look. Using our power series expansion, we did this and we did this, which is the Neumann condition for the flat bottom. That's done. That power series satisfies this equation formally and satisfies this one. We have now to satisfy these two, but here is the key thing. We have to set. We want to now we're going to do approximations, which is we want to satisfy this in the weakly nonlinear, weakly dispersive regime. So weakly nonlinear, weakly dispersive regime means first order in alpha and first order in beta. So, okay, so here I should write this. Weakly nonlinear. Weakly dispersive, which means order alpha, order beta, even though this is, so we're going to call this order epsilon. This also order epsilon, okay, with alpha small and beta small because it's weakly nonlinear, weakly dispersive. That means, in other words, I'm going to say the same thing in other words. That means I'm going to then get the first contribution in alpha and the first contribution in beta. That's why here, when I write this order beta squared in the notation of asymptotics, this means the whole tail of the power series expansion, the whole thing, right? It's a short way of writing. So you see, I'm only writing the first terms here in alpha and beta. Even though you can already see that this term here, alpha beta, is already second order. Because if alpha and beta are order epsilon, this guy here, beta alpha, is going to be order epsilon squared. Well, this guy's already squared. So the only guy that's going to matter here is this one. Okay? And note, please note that this is the first order. Look, if I do n equal to 0 here, this is 1, blah, 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 and no derivative, just f of x. Here it is. Okay? And actually, this guy here is sometimes called the reduced potential. It's not quite a potential, but basically the reduced potential because the derivative of this df dx at the bottom, which is this guy here, is the horizontal speed at the bottom. Right? The u at the bottom. So when I do the derivative in y, right, you differentiate this in y, just do that. Get the first terms, it's this. So you see order beta and order alpha beta. And the same here. So what I have to do now, right, to get my Boussinesq equation, which is my reduced system, my reduced model, is to plug this in to these to those equations and collect only the order alpha and the order beta terms. Okay? So this is what we're about to do. We have time. Good. Okay, substituting in the free surface equations, we have this. So technically speaking, I haven't done any approximation yet. Why? Because the whole series, the tail of the series is in here and in here, which means all the higher order terms of the series, I'm in this simplified notation saying these are the terms which are higher order terms, which are alpha squared, beta squared, and beyond. So if I called alpha and beta orders of epsilon, these are the terms in the power series which are the summation of epsilon squared, epsilon cubed, epsilon fourth, and so on. Okay? And of course, the simplification, the reduced modeling will be to throw these guys away. So you see, if I throw these guys away, right? If I throw these guys away, I am left with a weakly nonlinear, weakly dispersive problem. Right? So it's first order in alpha and beta, which means weakly nonlinear, weakly dispersive. Okay? Now, okay, so let me just better organize this. So we have a truncated, reduced model. Okay? Now I've made an approximation. I've thrown these guys away. And I have this system of equations for the wave elevation and the reduced potential all along the free surface. Right? There's no y in here. But this system is not good yet in the sense that Boussinesq, let me do a picture here again. Boussinesq was the first to reduce the problem, to study this problem. Okay, Boussinesq, he did something similar to what Korteweg and De Vries did. I mean, these are very, very talented, smart people, 1800s, know the math of the problem people didn't understand well, right? Knew the physics, and they said, okay, when the wave is long, and with respect to depth, they said the following. They said, look, there's basically no motion, no velocity in the vertical direction, very small, it's very shallow. And basically, the horizontal speed changes very little over the depth. So what they did is they got the equations, say all these equations, and they started doing averages. So they averaged over the depth. And Boussinesq deduced in 1890-something, I think it's somewhere in the notes. Well, I'll come to that, but 1800-something, he deduced the famous Boussinesq equations in an ad hoc manner. You understand what ad hoc means, right? Ad hoc, right? When you see in papers written like this, comes, I think, from Latin. Ad hoc means in a sort of a special way, in the sense it's not systematic. Oh, by inspection, ad hoc, okay? So he averages here, blah, 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 and he gets, I'm going to write soon, the Boussinesq equations. But then people later on tried to deduce the Boussinesq equations in a more systematic way. In the book where I think that's maybe the first place better explained, at least is Witham's book, which is a classic in waves, which is exactly what I'm following. Witham's book, he does what I'm doing right now. Okay, so Boussinesq uses then. Let me see what the notation is. Capital U. Capital U is of the average of the vertical average of the horizontal speed. Okay? Now, look this. dv dx, the f dx is this. Okay, convince yourselves. The df dx is the horizontal speed at the bottom. Okay? So what we need to do to, in a systematic way, not ad hoc. Oh, take this away. See, when it's ad hoc, for example, they would do, oh, this term here is physically should be bigger than that one, so just take it away. That's an ad hoc way. We're just trunking. Here, we did it by controlling powers of epsilon, so it's a little more systematic. Okay? So what we need to do, now we're going to try to recover Boussinesq's equation from this system. Here we have the speed at the bottom, okay? And also, look, here we have the potential, the reduced potential with no derivatives. So the first step is differentiate this equation with respect to x. So this becomes a speed, okay? And then we're going to try to switch, okay? Then we're going to try to switch from df dx to the average speed, which is capital U. Okay? So let's do this. So first, let U tilde xt define this as df dx, which is this guy here. It's the speed at the bottom is U tilde, okay? And then note the following. So from the series, so my hand starts getting tired. From the power series, we have that phi of x So look, this is just notation, right? So these are the first terms of the power series. So what did I do? I differentiated the power speed, the power series in terms of x, because I need to get horizontal speeds, and I am evaluating it at y capital, which is the free surface, okay? So that I can define the following. This is just notation, okay? Just notation. So now, a depth averaged speed, as Boussinesq did, is which I'm going to call this capital U. Okay? Do you agree? Capital U is the depth average. Look, this is y. the free surface. This is 0, right? This is y equal to y. This is y equal to 0. This is the horizontal speed from the definition of the potential. I'm integrating from the bottom to the free surface and dividing by the height of the fluid at that point. So this gives me the average velocity depending where I am. Do you agree? Right? I'm integrating, I'm summing the speed from 0 to the top and dividing by the height. That's the average speed. The average speed at that point. It could be a deeper point or a more shallow point. Who cares, right? So now, in here, substitute the series. So substitute the series. Okay, I'm going to skip some of the details. Let me just write here what comes up. There's one step in between the notes, no big deal. You don't even have to look at the notes, you can do it yourself. Okay, to conclude, and this is the fun. And finally, and this is the important thing we want. Why? Because now we have, see, this is capital U. Let me make it more exaggerated. So what I have now, I have the average speed this is the bottom speed, and they differ by an order beta term. See? So in the language of asymptotics, right, very simple asymptotics, the language is that the average speed is basically the bottom speed up to an order beta term. But since we are constructing, designing a reduced model up to order beta, we cannot forget this term. We can eventually forget this term. Okay? And then we have that, you know, think about this. This is a simple thing. We have that, basically inverting this relation, we have that so this is just a basically simple exercise in this concept. I mean, I will indicate it to you that we can change the relation like this. And this is what we need. So look, if U, right, if U is equal to this up to order beta, then you substitute, you can invert this relation and get that this is equal to that up also to order beta. And since our system, look, this is the same as this and is the same as this, right? And if I differentiate this equation with respect to x, it's this guy. So everywhere I'm going to put in yellow, look, everywhere I'm going to put in yellow, here, look, here, here, this one differentiated with this, right? And here, right, I have f of x, f of x, f of x, x with f of x, f of x, f of x. Everywhere you have this, substitute this, which is equal to f of x. And then, good, I'm almost in. And then we get, we have that, so we have then that this. Okay, it becomes this junk, right? Just substituting. But now the nice thing is that I have my equation in the same variables as Boussinesq. Okay. So we can do this. Okay, so let me actually show it to you. When I substitute, sorry, I went a little too fast. Not in the calculation, that's simple, just in the explanation. See, when I substitute this into that equation, I got these terms. Okay? No, wait a minute. I wrote something wrong here. Look. I forgot something. Please forgive me. Here, it's not the same thing. There's an XX here. I forgot. Okay? And then, of course, when I come back here, I have an XX here. Yeah, sorry. Just went talking and writing too fast, okay? Check that. So this one comes here from the series, okay? So you get the first guy and the second. Look at the derivatives come second. You got this guy. Then when you invert these terms in terms of utility, you get this. And here, there's a second derivative. So I didn't explain you how to go from here to here. Convince yourself. It's a little bit like an exercise, a very simple one. You basically plug in and this is going to give you, see, if you put one of these guys here, it's going to give you a beta squared, goes over there. Check that on your own. Okay, as an exercise. And then you get this. Then you plug this into the equations, you get that. And then you're going to get here higher order terms that you have to throw away. And that's basically the final thing I'll do today, right? So from this system here, since I'm doing a weakly nonlinear, weakly dispersive approximation, which means I will only keep order 1 in alpha and order 1 in beta, right? Here I put 0 because I was already thinking that I've dropped these terms. But when I do this substitution, I have more terms to drop, which I don't care, which are this, look. Alpha. When this multiplies that, I don't care, it's going to go away. Okay, so I only need to keep this guy times this guy times that, this guy times this, but not this with that. Right? And the same thing here in the bottom. I'm going to have a beta squared here. Throw it away. Right? And the final result, let me put it, I'm yellow, I put the final result. And I'll come back to this next class. The Boussinesq system is this. I'm almost there, right? What's the next thing I'm going to put here? Almost. But there's one fix that I'll leave it for next class. But I want to make a comment today still, which I find interesting. So this is the system, okay? And check this. Check alpha equal to beta equal to 0, which is the super simplification. Look what we get. Eta t plus u of x equal to 0, u of t plus eta of x equal to 0. The shallow water system we saw before, right? Now check just beta equal to 0. Eta of t plus 1 plus alpha eta u x equal to 0. U of t plus eta x plus alpha u of x, which is basically u squared over 2x equal to 0. It's the nonlinear shallow water system we saw before, which also which we can actually write in conservation form. We saw this before. So you see, everything sort of coming together. I'll come back to this. I went a little fast now at the end, so I could at least finish with this comment. So this is not yet the famous Boussinesq system. There's one minor fix I have to do, so it looks like the equation that Boussinesq did in an ad hoc way, saying, oh, this is big. He did everything correct, right? These guys had a very good physical mind and mathematical mind. Said, oh, this term is big. I'm going to average here. I'm going to throw that away. Pop, 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 pop. And the equation is the same. Okay, I'll come back to this next class, because now I'm rushing. Okay, so we'll stop here.